All right, so we're going to talk about quantum numbers in this video. Um, Quantum numbers came about when Bohr's model was not supported for larger elements beyond hydrogen and to a lesser extent helium. So, three scientists are known to have contributed to examining how electrons can move outside of orbits. Sorry about that. Um, Heisenberg, Schrödinger, and de Broglie. Heisenberg examined the idea that you cannot determine exactly where a particle is and how its momentum is going to allow it to continue to travel both precisely at the same time. You can know one of them or the other, but you can't know both of them exactly at a given moment. Schrödinger you developed a model where the electron was able to act like a wave. And we've spent a lot of time talking about that already this unit. And that's how quantum numbers came to be. And then de Broglie provided some support for that particles had properties of waves. We've seen that with his wavelength relating to mass. So this quantum mechanical model or electron cloud or wave mechanical model um, was developed in part by the work from these three scientists, that this idea that electrons can have characteristics of waves, and that these characteristics of waves, known as wave functions, can only have certain possible forms, and those are associated with specific energy values. They described these wave functions as orbitals, that basically they are going to account for 90% of the probability of finding an electron within that given space. So you can see there with 1s, with 2s, and with 3s, they are going to increase in size as the energy levels are increasing. So we said we were going to come back to these quantum numbers. Schrödinger attempted to came up with characteristics that would describe where each electron would be found within an orbital, and gave them a unique set of four quantum numbers so that every electron present outside of a nucleus would have its own unique set of quantum numbers. We have the principal quantum number, N, the angular momentum quantum number, L, the magnetic quantum number, M sub L, and the electron spin quantum number, M sub S. And we're going to talk about each of those on the next few slides. The principal quantum number is looking at it on a large scale, the size of the orbital and the amount of energy associated with that orbital. These are also sometimes referred to as shells, and they correspond to rows on the periodic table. Your lowest possible n is 1 for the first row on the table, and as of now, our highest n would be 7, but in theory, you would be able to go beyond 7 if you had electrons that were found higher than an energy level of 7. The larger your n value, the greater the size of the orbital, and the greater the energy that is found within that orbital. So L is describing the specific sublevels or the subshells that are found within our energy levels. It is used to describe the shape of these probability regions, the orbitals. S is spherical, P is more dumbbells, D is going to be found in a four-leaf clover kind of format, and then F is the double four-leaf clover and hula hoop split in half. So what you will notice is that in each of these orbitals, they are going to be assigned a specific quantum number L, and they will start with a quantum number of an L of 0. That's going to be associated with every S sublevel. And then all P's would be found with an L of 1, D's with an L of 2, F's with an L of G. If we kept going, the next one would have an L of 4, which is known as G, etc. So your L can go from anywhere from 0 up to n minus 1. So your first energy level only has one sublevel, S. Your second energy level has an L of 0 and an L of 1. It has an S and a P sublevel. Your third energy level has three sublevels, 0, 1, and 2, 0 up to n minus 1. So that would have an S, a P, and a D sublevel, and it just keeps going from there. Your magnetic quantum number is used to describe the specific orbital in which your electrons are likely to be placed, especially for these energy levels or sublevels, excuse me, that have multiple orbitals of equal energy. So it is describing which specific orbital the electrons have been placed in. And it can range from negative L to plus L. So if you are in an S sublevel, if you have an L of 0, the only possible ML you can have is also 0. There's only one orbital ever present in an S sublevel. If you are in a P sublevel, you have an L of 1, you can have an ML from negative 1 to plus 1. You can have three different orbitals. If you have an L of 2, your ML would range from negative 2 to plus 2, and you could have five different orbitals. And if you have an L of 3, your ML can range from negative 3 to plus 3, and that would give you a total of 7 orbitals. So again, the big picture is which energy level you're in. The sublevels are going to be your Ls. We're breaking things apart. Your MLs are your specific orbital within that sublevel. And then your MS is going to be the spin of your electron. Electrons, when they are placed in a magnetic field, are going to be able to spin in two directions, clockwise or counterclockwise. So we use ms to describe whether the electrons are spinning in a clockwise or counterclockwise direction, distinguishing between those two electrons in the same orbital, and they can have ms values of either plus 1/2 or minus 1/2. If you have a paramagnetic element or compound, they will have an attraction to a magnetic field because they have electrons that are not paired. You have solo electrons present in an orbital, while diamagnetic elements or compounds do not have any unpaired electrons and are not drawn towards that magnetic field. So we're just going to do a couple of elements showing their quantum numbers. So beryllium has 4 electrons if you find it on the periodic table. And so it has 4 possible electrons that would need to have a set of quantum numbers described for it. So if I was going to describe the 2 electrons in 1s, they each would have an n of 1 because they're in that first energy level. Their L would be 0, since your L can be your n, or sorry, 0 up to n minus 1. Your ML is your negative L to plus L. You only have one s orbital, so that's why your ML would be 0. And the only difference between those two electrons in the first energy level, 1s2, is that you would have one spinning clockwise and one spinning counterclockwise. For 2s, it's going to look a lot like 1s, but you would have, instead of an n of 1, an n of 2. Your L would still be 0 because you're still in that S sublevel, and your ML, because you have one orbital, would be 0, and your electrons would be spinning plus 1/2 or minus 1/2, clockwise and counterclockwise. Remember, however, that your second energy level, 2, can have L's of 0 up to n minus 1, so you could also, in theory, have an L of 1. And I believe we're going to see that with sulfur. We're going to focus on the electrons that are just found in that outermost energy level with sulfur, 3s and 3p4. So with 3s, whether it's 1s or 2s, it really doesn't matter what number is in front. The quantum numbers are going to be the same for L, ML, and MS for your 2s electrons. The only one that's going to change is your N. And then when we get to the 3p sublevel, remember again, you're still in that third energy level. So your L is going to be 0 up to n minus 1, and we said that p's are always going to have L's of 1. And so our 3p electrons would all be found in an n of 3 and an L of 1. Your ML is the specific orbital, and we always want to spread out our electrons so that each orbital gets an electron before we have to double up any of our electrons. So my first 3 electrons in sulfur are going to have the same N, the same L, but they're going to have different ML since they get placed into each orbital separately before they get doubled. And the MSs really don't matter as long as they are not the same for the 4th electron that gets placed. I just usually do the plus 1/2 first, but if you had put minus 1/2 on an assignment, I would not take off on that. There's nothing incorrect about whether you do the plus 1/2 or the minus 1/2 first. Our 4th electron would have the same N and L as all the other 3p electrons, but you would need to use one of the MLs that you have already used, because once you have put one electron into each of the orbitals in that sublevel, you have to pair up those electrons before you would be able to move up to the next set of higher energy orbitals. Because the -1 ml had already used an ms of plus 1/2, the final electron that sulfur has would need to have an ms of -1/2, clockwise and counterclockwise. So here you're being given 6 different designations, and I want to know which of these is incorrect. 1s, 1p, 7d, 9s, 4f, and 2d. So we're going to use our n's and l's to determine whether these are practical or not. With 1s, we know we would have an n of 1, and our L would be 0, and so that would make sense for 1s. That one's not a problem. But for 1p, you can't have an n of 1 and an L of 1. Your L always has to go up from 0 to n minus 1. So because they are the same, that is not a plausible orbital designation. 7d would have an n of 7 and an L of 2. And as long as you were at 0, anywhere from 0 to 6, that would be a plausible designation for a set of orbitals. For 9s, your n would be 9, your L would be 0. You can have a million s as long as you have an s and a number in front of it. You're going to have a plausible orbital designation because n will always be able to be up to, sorry, I'm not going to get this straight. N can be from 1 up to any number. That's a whole number. L can be 0 up to n minus 1. As long as your n's bigger than your L, you're good to go. In our second to last example, we have 4f. Our n would be 4 and our L would be 3, and that is definitely a plausible set of orbital designations as long as L was not the same as n. That would be correct. We're going to see in our last one, however, that n and L are the same. N is 2 and L is 2, and you can only have an L up to n minus 1. So that would be why that one was not accurate. So here I want to know which sets of quantum numbers are not plausible for the hydrogen atom, and then if they are not plausible, what's wrong with them? So you have an N of 4, an L of 3, and an ML of 4. Your N of 4 is no problem. As long as it's 1 or higher, you're good to go with N. And your L can be from 0 up to n minus 1, so an L of 3 is no problem. But ML has to range from negative L to plus L. And so that ML is too large to fit with those other two quantum numbers. So that one would not be possible. Here we have an N of 0, an L of 0, and an ML of 0. And we can stop without what L and ML are because we know our N has to be 1 or higher than that. It can never start at 0.